So let's take a look at how we use these characteristic curves, these family of curves, to do the analysis and set up the bias on our transistor so that we get the proper amount of amplification without going into distortion. So we use, again, that load line representation where we look at what's going on between saturation and cutoff. You obtain a graphical picture of an amplifier's operation by showing an example of signal variations on a set of collector curves with a load line. Let's assume that the DCQ point values are as follows. So we're going to choose the base current at 40 microamps, the collector current at 4 milliamps, and VCE, the voltage drop between the collector and the emitter, at 8 volts. The input signal varies the base current from a maximum of 50 microamps to a minimum of 30 microamps. The resulting variations in collector current and the voltage drop VCE are shown in the graph. The operation is linear as long as the variations do not reach cutoff at the lower end of the load line or saturation at the upper end. An amplifier that operates entirely in this linear region is a Class A amplifier, and we should not be in saturation then or distortion. So you can see how the representation then of the signal lies right in the center of the load line, centered on the quiescent point, or this 8 volts voltage drop from collector to emitter. Another type of amplifier configuration for the transistor is the common emitter amplifier. A typical common emitter amplifier is shown here. Again, you can see what we've got going on here as far as the representation. You can see we've got the load resistors set up, collector to emitter. We've got this voltage divider set up, R1 and R2, and we've got a input coupling capacitor to do a little bit of filtering. The one shown has a voltage divider bias, although other types of bias methods are possible. Capacitor 1, capacitor 2 on the input and output are coupling capacitors used to pass the signal into and out of the amplifier, such that the source or the load will not affect the DC biases. I mean, you can see what could be happening here is this output coupling capacitor could be attached to the input of another stage. Okay, so we look at these configurations of what's going on input to output. The capacitor C3 is a bypass capacitor. C3 shorts the emitter signal voltage AC to ground without disturbing the DC emitter voltage. Because of the bypass capacitor, the emitter is at signal AC ground but not DC ground, thus making the circuit a common emitter amplifier. So you can see that's why we call it common emitter. The bypass capacitor increases the signal voltage gain. The reason why this increase occurs is discussed. Notice that the input signal is applied to the base. The output signal is taken from the collector. All capacitors are assumed to have a reactance of approximately 0 at the signal frequency. Again, what are we looking for? We're looking for all of the energy to be coupled to the output. The bypass capacitor increases voltage gain. The capacitor shorts the signal around the emitter resistor, R sub E, in order to increase the voltage gain. To understand why, let's consider the amplifier without the bypass capacitor and see what the voltage is. Imagine the collector emitter amplifier, the common emitter amplifier, with the bypass capacitor removed. Okay, so again, let's go back here. That's that one right here on the output. As before, lowercase italic scripts indicate the signal or AC signals and signal alternating currents. The voltage gain of the amplifier is V out over VN. The output signal then, the output signal voltage then is V out is equal to that current resistor relationship. I sub C, R sub C. Again, you're going to see lots of these relationships in dealing with the transistor. So I hope you're writing them down and giving yourself some notes on what and why and where to use these. The signal voltage at the base is approximately equal to VB, which is approximately equal then to the input voltage, which again is approximately equal to I sub E by the sum of RE and R sub E, where RE again is the internal emitter resistance of the transistor. The voltage gain, A sub V, can now be expressed as V out over Vn. We've seen that relationship many times. We can expand it then to say, okay, well, V out is equal to the collector current times the voltage drop across the resistor, R sub C, and we just defined above Vn as I sub E RE plus the drop across the emitter resistor. Since I sub C is approximately equal to I sub E, the currents cancel and the gain is the ratio of the resistances. So they just defined that I sub C and I sub E are approximately equal to each other. So all we're left with then are the internal values here, R sub C over the sum of the internal resistance of the transistor and the drop across the resistor on the emitter. Keep in mind that this formula is for the amplifier without the bypass capacitor. If R sub E is much greater than the internal resistance, R sub E, then the gain, A sub V, is approximately equal to then just RC over RE. You might want to put that in your notebook. If the bypass capacitor is connected then across R sub E, it effectively shorts the signal to ground, leaving only R sub E in the emitter. Thus, the voltage gain of the common emitter amplifier with the bypass shorting, bypass capacitor shorting R sub E is R sub C over RE. The transistor parameter R sub E is important because it determines the voltage gain of a common emitter amplifier in conjunction with the collector resistor. A formula for estimating R sub E is given without derivation in the following equation. So they're saying you need to accept this. Just accept this as it's approximately equal to 25 millivolts divided by the emitter current. So if we look at a quick example here, determine the voltage gain of the amplifier both with and without the bypass capacitor. So we're just going to go through that exercise given the values and using the expressions that we just went through. So first, determine the internal resistance to the transistor at the emitter. To do so, you need to find I sub E. So we need to find the collector current or the emitter current. Thus, VB, V sub B, is equal to, we've seen that voltage divider relationship, so we're on the input, times V sub C, we get 1.75 volts. The voltage then across the emitter then is equal to VB minus 7/10. So we are taking that input value, that voltage, subtracting the barrier potential, and we get 1.05 volts. Now the emitter current is VE over RE. So we've got 1.05 over 1 k ohm. We get 1.05 milliamps. The voltage gain without a bypass capacitor then is, we just defined this above, The gain is equal to RC over the internal emitter resistance plus the drop over the resistor at the emitter. We get 4.59 as the gain. Again, look, no units. In decibel form, then we say AV is, so we go back to our relationship 20 times the log. So we're going to take 20 times the log of that unitless number, that figure of merit, multiply it, we get 13.24 dB. The voltage gain with the bypass capacitor installed then is R sub C over RE, as we've seen before, 197, quite a difference there. As you can see, the voltage gain is greatly increased by the addition of the bypass capacitor. So again, if we determine in decibels, AV is equal 20 times the log now of 197, we are at 45, almost 46 dB, considerably greater gain with the bypass capacitor. So when we come back, we'll take a look at phase inversion and the AC input resistance.